All right, let's get started. So in this lecture, I'm going to talk about one of the oldest and simplest of all models of the galaxy halo connection, abundance matching. And to lead up to it, I'd like to go into a little more detail about each of the different sort of flavors of the galaxy halo connection to give you a feeling for how abundance matching is distinct and related to sort of each of these comparable ways about going about predictions. So again, starting on the left of the sort of most computationally intensive, most predictive models of the galaxy halo connection are hydrodynamical simulations. So in these simulations, together with the gravity-only evolution of dark matter particle tracers, you also have baryon particle tracers that have not just gravity interacting, but also you're discretizing the Euler equation. So you include both their fluid dynamics, but also feedback processes that are not resolved by the actual simulation. So for any cosmological volume simulation, hydrodynamical simulations have to make assumptions for what physics is operative below the scales that are resolved. So for example, any attempt to be able to solve for the evolution of a gigaparsec box with hydrodynamics has no hope for the foreseeable future for any timescale that's professionally relevant to any of us to be able to make predictions for the collapse of a giant molecular cloud. And so for the timescale of our careers, we will need to rely on hydrodynamical simulations that have to make assumptions, empirical assumptions, for what physics is operative on much smaller scales than are resolved. And then the sort of free parameters that come along with those assumptions are then calibrated according to a combination of observational data and also calibrated according to insights from models of the galaxy halo connection. So these are the most predictive in the sense that hydrodynamical simulations predict the gas and stellar mass tracers and metallicity and just a rich variety of galaxy properties that you can then use to essentially make predictions for any galaxy tracer that you might observe. But they are extremely expensive, and because they are sort of intrinsically uncertain with the feedback prescriptions that need to be adopted, it's difficult to sort of rigorously explore the full parameter space of this uncertainty, because each time you have a new model, or even each time you just want to vary the parameters, you have to run an entirely new hydrodynamical simulation. And so even very simple models like abundance matching, which I'll show you, can sort of give very helpful guidelines for the way in which these prescriptions of baryonic feedback need to be tuned in order to be able to make broadly reasonable predictions. So next up in the line of sort of in this landscape of galaxy halo models are semi-analytic models. So in these models, they directly use merger trees from a gravity-only n-body simulation. And there's a particular way in which sort of all semi-analytic models make their predictions. So you make some assumptions for the physics that's thought to be operative for a set of reservoirs of mass and energy and momentum. So for example, a hot gas reservoir and a cold gas reservoir and a stellar mass reservoir. And a coupled system of ODEs regulates the transfer of energy and mass and momentum between these different reservoirs. And on a halo by halo basis in a simulation, you solve these ODEs to be able to make predictions for the properties of the galaxies that lives in that halo. So there are many different varieties of semi-analytic models which are sort of focusing on different regimes, capture different physics. All semi-analytic models are mathematically structured in this way. You have a coupled ODE system that you solve on merger trees on a halo by halo basis. So they are highly predictive. They make predictions for galaxies of essentially all of the galaxies in the universe. So if you run a semi-analytic model on a cosmologic simulation with merger trees, then you can make predictions for ELGs and LRGs and luminosity selected galaxies, et cetera. And they are much cheaper than hydro simulations by a couple orders of magnitude, depending on details, but they are still more expensive than sort of simple empirical models like abundance matching that I'll show you. And so it's still challenging with semi-analytic models to, for example, do an exhaustive MCMC parameter walk through your unknown parameters of your galaxy formation physics model. So Semi-empirical models are a newer class of models that try and so go one step from SAMs towards empirical models that still attempt to retain a lot of the predictive power of SAMs. In that, for example, semi-empirical models predict galaxy star formation histories, but they adopt sort of empirically motivated approximate prescriptions. Essentially, you can think of semi-empirical models. So eMERGE is sort of one of the first of this class of models. Universe Machine is one from several years ago. Sort of DiffSky is a model I've been working on for the past several years that all sort of operate in the same basic way. You make sort of empirically motivated prescriptions for essentially the solutions that emerge as a result of solving these ODEs and SAMs. Rather than solving ODEs themselves. So in this way, semi-empirical models are significantly faster than SAMs because they're not solving ODEs on a halo-by-halo basis. But they are still using merger trees. And so they capture some of the complexity of semi-analytic models, but they rely on these approximations, so they're much faster. So this is the semi-empirical models are just a trade-off in this, or just another flavor of trade-off in this between sort of computational complexity, computational demands, and sort of physically realistic levels of complexity. That's most of what I will have to say about Hydro, SAM, and semi-empirical models for purposes of these lectures, but I'll make connections from empirical models that sort of give insight and constraints into SAMs and Hydro SIMs throughout these lectures. Okay, so that brings us to the next sort of class of models in this landscape of complexity, subhalo abundance matching, or SHAM. And so here's the basic way in which SHAM models proceed. So the idea is to paint a stellar mass or a luminosity onto every halo and subhalo in a cosmological box. And so here I've drawn a schematic of a host halo, which is a sort of a host halo is just a dark matter halo unto itself. It's not found inside some larger halo. And a subhalo is also a gravitationally self-bound halo, and it happens to fall inside the boundary of a larger halo. So there were several questions in between lectures about this particular choice of virial radius, or of the radius or the boundary of a dark matter halo. And it's worth pointing out just that the choice that you make for the radius of a halo does impact whether or not, for example, this subhalo will be called a subhalo or will be called a host halo. As we'll see a little bit later in this lecture, that particular definition has, for modern implementations of SHAM, has a relatively small effect on the predictions of the model because of the way in which subhalo properties are connected to galaxy properties. But that definition is important, so we should keep in mind that the choice of the virial definition is actually, you can think of it as a hyperparameter of the model. It's a choice that you make in advance from which your predictions flow. So SHAM so the concept of sort of central galaxies and satellite galaxies is directly connected to this choice towards this concept of host halos and subhalos. So central galaxies sit at the dead center of a host halo, and satellite galaxies sit at the dead center of a subhalo. SHAM is a non-parametric technique. So there are hyperparameters that are chosen in advance, and then there are no or very few free parameters of SHAM. So we'll talk about this a bit more in a second, how this proceeds, but the basic idea is to derive a non-parametric mapping between halo properties and galaxy properties to be essentially sort of minimally parametric in a sense that I'll define in the next couple of slides. Yeah, so finally, SHAM is distinct from halo occupation models. This is the cheapest of all galaxy halo connection models. In halo occupation modeling, you completely ignore subhalos. You do have satellite galaxies and central galaxies, but satellite galaxies don't sit on subhalos. They are sprinkled in according to an analytical prescription. So the HOD is the halo occupation distribution, and the CLF is the conditional luminosity function. So these are different prescriptions for being able to sprinkle in both centrals and satellites into host halos. So these models were born at a time when subhalo finding was still either immature or non-existent. And so at that time, these models were born essentially when we had just been able to run cosmological simulations and reliably be able to make predictions for a host halo mass function. And so halo occupation models sort of ask the least of the simulations. They don't ask the simulation to be able to confidently resolve subhalos or subhalo structure. And instead, they have free parameters that then are then tuned to observations. For example, for how satellites should be distributed within halos and what should be the mass to light ratio. This is parametrically encoded in halo occupation models. Okay. Right. Okay. So much for the landscape, and now I'd like to focus specifically on sham for the rest of this lecture. So here is the key ansatz of abundance matching. And it's very, very simple. It's just that the deeper the potential well that your galaxy lives in, the more massive the galaxy, or the brighter that the galaxy is. So this principle is really, it's the only principle that's really at work. This is the only sort of physical ingredient or ansatz of the model. And the rest of sham predictions follow from the fact that you couple this prescription to a cosmological simulation. And so this is true. This is assumed in sham sort of all the way up and down the line, from low mass galaxies to high mass galaxies. You have small galaxies live in small halos, larger galaxies live in larger halos, all the way up and down the line in a monotonic relationship on average. So here's the key assumption of sham. So the question is, fine, okay, so my dark matter halos should be monotonically related to my galaxy masses. Halo mass should scale like galaxy mass. But what should that scaling relation be? So I think sort of the key inside of the formulation of sham is just that whatever that scaling relation is, the thing I want to get right is the galaxy luminosity function. Or if I'm going to paint stellar mass instead of luminosity, the thing I want to get right is the galaxy stellar mass function. So I want to make sure that that is a bang-on prediction of the model. And I want to do that in a non-parametric way that guarantees that to be the case. So that's actually a very straightforward thing to do. So if you simply rank order your halos by mass, and then you rank order your galaxies by their mass, then you can essentially set up a lookup table interpolation to just directly read off what the halo mass is that should host this galaxy and this galaxy and this galaxy. And it really is that straightforward with sham. So neglecting for a brief moment the role of scatter in this relationship. In the absence of scatter, you literally when implementing this in code, you create a lookup table that have some volume limited sample of galaxies, and you just you sort them by mass. And you have a catalog of dark matter halos from your simulation that are sorted by mass. And then you just map directly the abundance of this galaxy corresponds to the abundance of this dark matter halo, and that lets you directly read off its mass. So this is not a heuristic. It's actually the way that this model proceeds. And in this way, you can then paint onto a catalog of dark matter halos the stellar mass of a galaxy that lives in that halo. I'm slightly abusing terminology, so I apologize if this is confusing. When I refer to a halo, in this context, because it's subhalo abundance matching in particular, I mean halo or subhalo, grouped together, ranked by their mass. I'll try, whenever I mean an isolated halo unto itself, I'll try to use the term host halo so that there's no confusion. But it's essential for the formulation of sham that host halos and subhalos are treated on an equal footing when they're sort of rank ordered. So this is a key feature. Yeah.
Yeah, so would it be that much more complicated to have a more realistic situation where smaller galaxies can live in more massive halos?
So any modern implementation of sham has scatter about this relation. And the scatter can be significant, especially at low mass, where low mass halos are preferentially more impacted by their environment than very high mass halos. So if you're a 10 to 15 solar mass cluster mass halo, you don't care anything about your environment. The only thing that really matters to you is the environment that you occupy. But if you are a dwarf, 10 to the 10 solar mass dark matter halo, it matters a lot where you live in the density field. And so because of that fact, you can even just intuitively get a sense that there should be a lot more scatter in the stellar to halo mass relation. at low mass than there is at high mass. And so, in fact, this relation does come with a lot of scatter, and you can have low mass galaxies that live in higher mass halos. With that said, it is not obvious that this scaling relation should be as tight as it is. Yeah, for me, the successes of sham that I will show you shortly are still very non-trivial and very non-obvious. So it's easy to imagine a universe in which this was not true. But that's not the universe that we live in, as I'll try to convince you. So
Thanks.
So how do you get that stellar mass function specifically?
yeah, so both your halo mass function and your stellar mass function come come directly as inputs. So for example, the way you might do this if you were going to make predictions for SDSS galaxy clustering would be you would take a volume limited sample of SDSS galaxies, and you would rank order them by their mass or by their luminosity. And so then you literally read off the luminosity of the galaxies in your catalog.
But then it's something you measure from photometry. I'm speaking more from the astrophysics side. This is something I don't know personally.
So for example, say you do this in the R band or in the I band, then you will get a different relationship between halo mass and R band and halo mass and I band. You can think of that like a pre-choice for what you're trying to predict in advance. So sham is fundamentally a one-parameter model, and so it does not allow you to predict UGR-ZY for a galaxy sample. The goal is to be able to make a prediction that's sort of anchored on a particular chosen galaxy property for galaxy mass. That could be stellar mass from an SPS fit, or it could just be breast frame luminosity in a given band. Let me keep moving for a bit before we do more questions. I want to show how this works for sort of why this is a predictive thing to do and not just a sort of trivial thing for mass pain. Then we can come back to your question. So by construction, sham automatically gets exactly correct the luminosity function. It's put in by hand. It's a direct ingredient from a given choice of the galaxy sample that you're trying to make a prediction for. And sham only makes a prediction for a particular luminosity band or for a particular definition of stellar mass. But then when it comes time to make predictions for other things, like for example, how do galaxies cluster as a function of luminosity? Well, all bets are off. So at no point has sham sort of hardwired in correct predictions for galaxy clustering. The only thing you're getting right by construction, let me just generalize a little bit, is some particular one-point function, like a luminosity function or a stellar mass function. A one-point function is being a generic term for something that can be computed with a histogram. So all spatial statistics are then actual predictions of this model. And so this is a very non-trivial sort of success of this prediction. So this is from a paper led by Charlie Conroy in 2006, in which what he did was he did this rank ordering exercise for SDSS galaxies on the left and for deep 2 galaxies on the right. Again, constructed volume limited samples of galaxies, and then made prediction for the 2-point clustering. So every little panel of this slide shows as a function of spatial separation, it shows the 2-point function on the vertical axis. And so the points with error bars are the observational measurements. And you can see in different panels, you have different luminosity samples. And then the black solid curve going through the data points is not a fit to the data. It's a prediction of the clustering and its dependence on luminosity. So this was true at low redshift. This is true at high redshift. This was one of the sort of foundational results in the field. And Charlie was so happy about this result. He has, I think, at least I credit him with the most famous footnote in the field of galaxy halo connection. So you can see he has this concluding sentiment that overall the agreement is excellent on all scales and for 4 samples, and is a one-word footnote. Booyah. The referee, my understanding was the referee contested this and thought this was an inappropriate language for a scientific publication, but Charlie pushed back. And he says that no other word in the English language can quite so succinctly capture what a big deal this result is. And the referee acquiesced. So this is in the publication. And it really is a non-trivial result. So the 1-point functions are put in by hand, but to get the luminosity dependence of the clustering on both small scales and large scales is highly non-trivial. So I really think it's no exaggeration to say that this is a foundational result in the field. It gives great confidence that the fundamental tenet of abundance matching is in some level correct, that there's a tight scatter scaling relation between halo mass and galaxy mass. So Okay, great. I wanted to get to that point before I broke again. I think we had at least one question that I postponed. So yeah, please.
Yeah. So when you said you do this for both halos and subhalos, do you do this sort of like 1:1 mapping for the host of the subhalos to the most massive subhalo? Like is the most massive halo the host of the most massive subhalo, which might not necessarily work, right? Because if you have, say, a 1:10 merger event versus a 1:1 or 1:2 merger event, that's going to be completely different for the subhalo abundance mapping, I guess.
Right. So for models, sort of modern implementations of models that sort of work this well, this is actually even true of Charlie's model. You choose the mass of the subhalo at the time of infall, when it was still a host halo unto itself. I'm going to come to that in just another slide with the way that that works and sort of why that's important. It is a critical detail for getting this right. So because you're right, it's completely ambiguous as to sort of which particular mass for the subhalo you should choose. For host halos, it's not so ambiguous, but for subhalos, there's sort of many different choices that you might make, and it's not obvious which one is correct. The way in which modern models are implemented, I think, sort of disambiguates that. I'll come to that in just maybe one or two more slides. Yeah. Okay, one more question.
How does sham do with higher order correlations, like 3-point and so on?
Let's see. I have several slides that will show beyond 2-point function results for sham. The short answer to your question is it does very well. For example, galaxy group catalogs are a morass of many different endpoint functions that are combined together in summary statistics. And sham makes very good predictions for galaxy groups, for example. But galaxy clustering, redshift space distortions, I'll show many more results later beyond just this. So, yeah. Okay, great. Okay, so an aside on the way in which we make predictions. So everything I've been showing you for subhalo abundance matching is based on simulation-based predictions. So by this, what I mean is your input is a cosmological box, essentially a dark matter halo and subhalo catalog, and you directly paint galaxy properties onto halos and subhalos in the catalog. So this is not the way that sort of historically many different models of the galaxy halo connection have been implemented, and even present day models based on generally when people refer to the halo model, they typically mean a sort of analytical prescriptions for the abundance and clustering of dark matter halos, neglecting anything to do with galaxies. And then you can analytically write down, once you sort of know, say, analytical fitting functions for the dark matter halo clustering and abundance and internal structure, well then with additional analytical prescriptions for your galaxy halo connection, then you can work out predictions for the 2-point clustering of galaxies from the 2-point clustering of halos. For subhalo abundance matching, there do not exist analytic prescriptions for the abundance and particularly the clustering of dark matter subhalos. Those sort of analytic fits have all been calibrated based on host dark matter halos for some years. But really the choice that you have available to you really for subhalo abundance matching is direct simulation-based predictions. This has other advantages beyond halo model approximations. Halo model is notoriously difficult to be able to make sort of accurate predictions for particularly the bias function and its scale dependence, especially near the so-called 1-to-2 halo transition regime. So in the regime where this imaginary boundary actually becomes important, it's very difficult to calibrate a fitting function that sort of captures the complexity that you can directly get in simulations just by using simulations directly. And so for most of this talk, and for most of the talks, most results tomorrow, I'll be talking about sort of simulation-based models. But I did want to just at least mention the halo model is still very much alive and well, and historically has been a key ingredient towards being able to have a sort of root level understanding for simulation-based results. So, okay, so how do we make predictions with simulation-based models? A sort of pro of simulation-based models is that it's very straightforward to be able to make predictions. So you have an input dark matter halo and subhalo catalog, and you have some scaling relation for the relation between, say, galaxy mass and stellar mass, like the one that you get from abundance matching. And you make some assumption for what the PDF is. So for example, where is the scatter about that relation? And then you just draw from a log normal and then paint that drawn value onto every subhalo in the catalog. So it's very, very fast. And to be able to make predictions that you can then go out and make and then compare to observations. For the case of the stellar mass function, it's very, very straightforward. You know the box size. And so you just compute a histogram for the number of galaxies that falls inside a given stellar mass bin. Divide by the volume, this gives you the number density that can be compared to your number density in a volume limited sample of galaxies. So simulation-based predictions for the stellar mass function are sort of very straightforward to work out. The same is true for two-point clustering. Again, the sort of, let's rinse and repeat, but for the two-point function. So you draw from some, say, log normal centered at your particular value of stellar mass, paint it onto your galaxies, bin your galaxies according to however you're going to bin them to measure your two-point function in the data. But now we will measure the two-point function directly in the simulated box. And again, it's just a pair counting code that then tells you the number of pairs of galaxies separated by a given distance from each other, from which you transform into a two-point function. I've given a link to several different sort of widely used correlation function codes. The sort of industry has many of these now. These are a few of the ones that I use. So CoreFunc is definitely the fastest code in the field for very, very rapidly computing two-point functions. Halo Tools is a library that I developed. It also includes a bunch of different two-point function calculators with a bunch of different varieties like weighted pair counts, et cetera. TreeCore, for example, is a nice code for doing these two-point function calculations in angular space, for example, if you want to make predictions for light cones. But there are many sort of, the field now has sort of many of these techniques because simulation-based modeling is now so common for galaxy halo connection models. Okay, so now to come back to the question that I sort of postponed answering. So this figure sort of illustrates the following exercise. So go into your catalog of halos and subhalos, rank order the halos and subhalos according to present day mass, instantaneous mass, make a cut at some given choice in number density, and then just compute the two-point function. Just use your pair counter to compute the two-point function and plot it as a function of scale. That's what's shown with the orange curve. And the blue curve shows the same exact result, but instead of rank ordering by present day instantaneous mass, you rank order by peak mass, the largest mass that the halo or subhalo ever had in its history. So for subhalos, because of subhalo mass loss, that's generally a larger number than the present day mass of the subhalo. And so these are inequivalent predictions. So why is it that we see stronger clustering for the M-peak based model, especially on small scales? And it's everything to do with subhalo mass loss. So we're looking at in this figure as a function of, you can think of this as time since infall. It's actually the accretion redshift for redshift 0 halo on the horizontal axis. This is the average mass that's lost by a subhalo after infall. And you can see that after delta Z accretion of 1, the subhalo has lost 80% of its mass. This is, oh yeah, I did link to this. Yeah, this is from a paper by Frank Van den Bosch several years ago. So you can see directly that subhalos lose mass like crazy as soon as they fall inside the viewer radius of some host halo because there's strong tidal forces that act on the subhalo. And so Frank has this nice rule of thumb in this paper that essentially after you make your first paracentric passage as a subhalo, you lose 80% of your mass. Yeah. So what does this have to do with abundance matching? Well, the radius of a galaxy is tiny compared to the radius of a dark matter halo. And when a subhalo falls into a host halo, it sloughs off mass from the outside because this is the most loosely bound material to the subhalo in the first place. And so yes, it's losing tons of mass, but it's not shedding galaxy mass nearly at the same rate. And so that means if you want to make a prediction for how much galaxy mass should be in a subhalo, well, if you directly tie it to the present day mass, then you're going to way overpredict how much mass has been lost by the subhalo over time because it sheds all this mass from the outskirts while it leaves the central galaxy, while it leaves the galaxy at the center of the subhalo untouched for a while, for gigayears. And so that all this adds up to modern implementations of abundance matching. Choose M-peak as their, or M accretion as their ranking property rather than the instantaneous mass. And this is critical in order to get two-point clustering, right? And then even a little more detail Vmax is actually the property that, for example, Charlie used in the famous Booyah result. Vmax is the circular velocity, is the maximum value of the circular velocity profile of the halo, which for an NFW profile, it's about 20% of the virial radius. So again, Vmax is a way of thinking about and quantifying the potential well depth of a halo that's defined by a radius that's much closer to where the actual galaxy lives. And so in detail, if you want an accurate prediction for subhalo abundance matching, then you need to choose a particular halo ranking property that's insensitive to this initial phase of mass loss by a subhalo that probably doesn't have much to do with the mass of the galaxy that sits at the center of the subhalo. What you're looking at here is a fairly exhaustive exercise in a paper led by Rachel Reddick in 2013, in which she made a bunch of different comparisons of subhalo abundance matching to 2-point clustering measured in SDSS. So what she did was she rinsed and repeated the exercise that I just described of rank ordering, adding some scatter, and then making 2-point clustering predictions. So that's each panel shows as a function of spatial scale the 2-point function. But she repeated this for subhalos ranked by M peak, by M at accretion, by V peak, by V at accretion, by instantaneous mass. And this is really the paper that I think sort of gave rise to V peak as the sort of most successful of the abundance matching rank ordering predictions, because the V peak curves in this figure are the ones that essentially go straight through the SDSS data points. Let's see. Running a little short on time. The satellite fraction plays an essential role in this prediction. So the idea is that when you make this cut on number density for halos ranked by either M today or M peak, you would throw out more and more subhalos if you use instantaneous mass because of all their mass loss. And so the choice of subhalo ranking property strongly affects the satellite fraction. How many subhalos make it into your sample versus host halos? This is, as you can see in this figure, different satellite fractions are color-coded on the right, and the left panel tells you how that impacts the 2-point correlation function. Generally speaking, high satellite fraction means very strong clustering on both large scales and on small scales especially. I'll skip over this. This is really just the same result from Rachel Reddick's paper that shows how these different choices of abundance matching ranking properties correspond to not just changes in clustering, but also the satellite fraction. She found this was really one of the defining features of this choice of subhalo property that sort of gives you good results for 2-point clustering. And then last, from this really nice paper, this is really so this is one of the classic papers on that sort of I think gave rise to the modern form of abundance matching. Varying prescriptions of scatter were added to this relation. So scatter of essentially 0 and then increasing large amounts of scatter in the stellar to halo mass relation. You can see the orange curve is the prediction when you just have 0.3 dex of scatter in the stellar to halo mass relation from abundance matching. And it's grossly off of the 2-point clustering relative to tighter scatter models. So this is another, I think, key result from galaxy halo connection that sort of tells us that the connection between galaxy mass and halo mass is just fundamentally very tight. There's just not that much room for scatter, even though there's enormously complex physics that sort of give rise to how much mass is in a galaxy. There's really only room for maybe 0.2 dex of scatter in the stellar to halo mass relation. Okay, as promised, here are some other results beyond just projected 2-point clustering. So you are looking at, in the left-hand panel, this is predictions for redshift space, monopole and quadrupole in a paper led by Joe DeRose, in which he again used sort of standard V-peak-based abundance matching to look at Z-space correlation functions, again compared to SDSS. And then on the right, this is a prediction of abundance matching for galaxy-galaxy lensing. So you measure the excess surface density profile in simulations and then directly compare that to the galaxy-galaxy lensing signal SDSS. And again, you have very good predictions with essentially this no free parameter model. And for a few more minutes, I'd like to just quickly sketch sort of ways in which abundance matching can be extended to give more complex predictions for more complex galaxy samples. Abundance matching really only makes predictions for one galaxy property at a time, but conditional abundance matching is a variation on this technique or an extension on this technique, which allows you to be able to make predictions for two joint properties of galaxies at the same time. So in this variation that I'm showing in this figure, I'll show how galaxy clustering and its dependence on color can be predicted with a variation of abundance matching called conditional abundance matching. And the key idea of conditional abundance matching is just at fixed halo mass and at fixed galaxy mass, you make this other assumption that there's a monotonic correspondence between, say, galaxy age and halo age, or between galaxy star formation rate and halo mass accretion rate. And again, there's just this monotonic up and down the line scaling relation that's assumed, where it's a purely non-parametric scaling relation. You say, I don't know what that scaling relation should be, but I know what I want to get right is the color PDFs. And so then if I apply this ansatz at fixed galaxy mass and at fixed halo mass all the way up and down the line, well, then I can then paint values, in this case of G minus R, onto my subhalo catalog. And the results for the predictions for two-point clustering are, again, unreasonably good. There's strong dependence of two-point clustering on galaxy color at fixed luminosity. And just by this simple ansatz that older halos host older galaxies and younger halos host younger galaxies, in remarkable level of detail, without free parameters beyond what you need in order to sort of by construction get the one-point functions correct, the color dependence of two-point clustering comes out correct. So conditional abundance matching has, and so here's an example of a highly higher order, of a highly beyond two-point result, in this case of conditional abundance matching. So you're looking at the quenched fraction of galaxies. So what fraction of galaxies has star formation rates less than 10 to the minus 11? Specific star formation rates. And as a function of group-centric radius, what is that quenched fraction? In groups, rich groups, and clusters. So this is a higher order statistic that just essentially comes out as an emergent prediction of conditional abundance matching. So, okay. Wrapping up, so conditional abundance matching and the sort of many variations I think that exist on this technique, I think is still a frontier of sort of abundance matching approaches to the galaxy halo connection. There's now many variations, including some very recent ones that give some really sort of excellent predictions for mock galaxy catalogs and their dependence on multiple colors at once. Let's see. Other frontiers of abundance matching are sort of extensions to be able to make predictions for non-trivial galaxy samples, like, for example, ELG galaxy samples are selected by strength of a given emission line. And Sarah Ortega-Martinez has very recently been working on new techniques to be able to extend abundance matching to make predictions for ELG samples, which has been very successful. Let's see. Ismael Mendoza, a graduate student at UMichigan, has a very nice adaptation of conditional abundance matching he called multicam, which has capability of being able to make predictions for multiple galaxy properties at once as a function of multiple halo properties. For me, this is a very new result and a sort of new direction for conditional abundance matching. I think is very powerful, and I think will continue to be predictive in coming years. So let me just conclude, maybe with a couple minutes for questions. So I've sort of reviewed the landscape of models of the galaxy halo connection, from the very computationally intensive hydrosims all the way to sort of halo occupation models. And subhalo abundance matching is slightly more computationally intensive than halo occupation models because it uses subhalos, so it does ask more of the simulations. But by asking more of the simulations, you get a lot more from the model without new free parameters. So by leveraging the fact that galaxies live in subhalos, you get an enormous sort of gain in your predictive power without having to have a proliferation of free parameters. And maybe I'll just sort of conclude with my sort of big picture takeaway from SHAM in general. It's really just that the galaxy halo connection is fundamentally simple. It emerges sort of naturally from very complex physical processes that regulate galaxy formation. But the scaling relations that come from the connection between halo mass and galaxy mass are sort of strikingly simple given how complex galaxy formation physics is. And so this gives a lot of, I think, confidence that we can apply models of the galaxy halo connection as part of our cosmological inference pipelines, be able to make predictions for galaxy clustering that then tell us about cosmology. So, yeah, that'll just conclude. Thanks.
Thank you, Andrew. So questions?
I have a question about Sham. So you can apply the technique to derive like the mass halo to like the luminosity of the galaxy, like to create a map between the mass and the halo and the luminosity. So I was wondering if like Sham also has like the potential to like derive like the IMF of like a luminosity or like
The IMF. So I think you're asking whether the initial mass function, which tells you from a collapsed gas cloud, the abundance of stars as a function, individual stars as a function of their mass.
yeah. So it's like in a more general like question, like to get the information, the specific information about like the what is the luminosity of the galaxy, like the specific like components, such as like the distribution of stars and stuff like that.
I don't know a way to use sham to infer the abundance of stellar mass as a function of stellar age. I don't think that means it's impossible. I think historically that's definitely not what sham. That's definitely outside of the scope of sham. But the scope of sham is changing. For example, Ismail's multicam, I think, is very predictive and could be adapted to make much more complex predictions. So I would say one of my themes from these lectures is just that this field needs new ideas. Predictions in the nonlinear regime have lots of systematics, and even though I don't think that traditionally sham has that within its scope, you may see a way to do it, and so
Hopefully.
that may be fruitful thought. So
Right.
Thank you for the nice talk. I had a question about, you mentioned that the sub-halo, when it passes into a way far bigger halo, loses a good portion of its mass, if I understood correctly.
yes, yeah.
Does the diameter of the halo itself change? And also, is there an effect on, for example, the strong lensing you might be observing, or even the observables that you might be looking for in these subhalos? Yes,
great. So yes, when a subhalo falls inside the Vireo radius of a larger halo, its radius shrinks as its mass shrinks. And you asked about, for example, small scale, very small scale lensing,
Correct.
strong lensing or otherwise. It's for that set of predictions, it's actually the instantaneous mass that's the important thing. It's not the mass that it may have had 2 gigayears ago. Because the mass that it has right now is the mass that affects the geodesic. So the thing that you actually observe with subhalo lensing or with small scale lensing is the instantaneous mass of the subhalo. So this using the accretion mass or the peak mass, I think, is more relevant for predicting the stellar mass that lives in a galaxy than the lensing profile around the subhalo. So.
Okay, so that brings up another question in that case is, if we wanted to observe this effect of it losing mass as it's entering this bigger halo, would it be possible to have an observation of this happening? For example, when the instantaneous moment, I guess, as this subhalo is falling into a bigger halo?
I think not. So it turns out that so there are many ways in which you can go awry by taking literally the Vireo radius as something physically real. So for example, subhalos begin to lose mass long before they fall inside the Vireo radius of a halo. So I actually have a link to a paper led by Peter Baruzzi showing, in which he showed that actually the time in which a subhalo's mass peaks is typically around 3 times the Vireo radius. And that's really just because this spherical Kauer assumption is really only so accurate. It's really just an approximation so that you have some mass proxy that you can use to quantify potential well depth. But in reality, the density field is very complex and nonlinear in the whole area surrounding a given halo. And so mass loss begins long before the halo crosses the Vireo radius.
Okay, perfect. Thank you.
Okay, I think it's a good time for a break. So 20 minutes. Okay. Yeah, half an hour break. Let's thank again, Andrew.